Good morning, everybody. This is the engineering mechanics module, and this is lecture number 8, the rectilinear kinetics of particles. Um, we've started studying the dynamics part of this module, where we study the kinematics first, and then we are now studying the kinetics. And these are the two branches for the dynamics. So the first branch, the kinematics part, we were studying the motion of a particle, either moving in a straight line, which is called the rectilinear motion, or moves in a curve, or follows a curve, which is called the curvilinear motion. And now we'll study the second part of the dynamics, which is the kinetics. So the kinetics here is the study of the relations between the unbalanced forces applied on the particle and the resulting changes in motion. So previously, when we were studying the kinematics part, we didn't take into account the forces at all. We were just studying the behavior of the motion in terms of the position, velocity, and acceleration. But now, if we started to take into account the forces, either the external forces applied on the particle or the forces generated due to the motion, so we are studying the kinetics part of the dynamics. So if we have a particle, and this particle is subjected to unbalanced force, so this particle will start to accelerate. So the figure here shows a particle on the left-hand side of a mass m, and this particle is subjected to three different forces in different directions. So we have a force F1 going to the right, we have another force F2 going to the left, and we have an inclined force here, F3. So the resultant force coming from these three forces is called the sigma F, where sigma F here is positive, so it has a positive value. So as a result, the particle here starts to move in the same direction as the force with an acceleration a. So the sigma force here is what we call unbalanced force. So the unbalanced force here that generates the acceleration of the motion is sigma f, and it is coming from uh, all the applied forces on the particle. So in this case, the particle is governed by what's called the Newton's second law. The Newton's second law says that the resultant force, sigma f, is equal to the mass of the particle multiplied by a, which is the acceleration. Sigma f is the resultant force, and it is measured in Newton. The mass of the particle m, which is measured in kilogram, and the acceleration of the particle that is measured in meter per second squared. We have generally in the dynamics, we have four units. We call them SI units because we are following here the SI units, the International System of Metric Units, and they are shown in this table. So the first three symbols here, the first three quantities, the mass with a symbol M, capital M, the length with a symbol capital L, and the time with a symbol capital T. These three quantities are called the base units in the SI system. The mass is measured in kilogram, the length is measured in meter, and the time is measured in second. The fourth unit here, which is part of the SI units, is measured in Newton, and the Newton here is derived from these three units, these three quantities. So if we, for example, try to get the units for the force based on the Newton's second law, so the force is equal to the mass multiplied by the acceleration. So the units of the mass is kilogram, the units of the acceleration is meter per second square. So, excuse me. So the kilogram multiplied by meter by second squared is Newton. So just this, the Newton's second law was verified several times experimentally and can be verified using what's called ideal experiment. So if we have a mass particle and this mass particle is subjected to a force F1, the magnitude F1 in a specific direction, and if we are able to measure the acceleration of this particle under this force, so the acceleration in this case is called A1. So if we take the exact same particle and subjected this particle to another force called F2, so this force will accelerate the particle with an acceleration of A2. So if we keep repeating this experiment, we'll find out that the ratio between the force and the acceleration is constant. And this constant is called the inertia or the particle's inertia. It is obviously defined as the resistance of the particle to the motion or the resistance of the particle to the resistance of the particle to the change in the velocity, the rate of change of the velocity. And it can be written as F1 divided by A1 is equal to F2 divided by A2, and so on. So it's F divided by A is equal to constant C. So all the time we get the same constant. So in this case, this constant C is the mass of the particle. It was found that the constant is the mass of the particle. So this Newton's second law is written as the force, the resultant force applied to the mass is equal to the mass multiplied by the acceleration. F is equal to ma. Generally, in studying the dynamics, we have two systems of units. The first one that we are using and will be using in this module, it's called the SI units, the International System of Metric Units, where the mass is measured in kilogram, the weight is measured in Newton, the length is measured in meter, the time is measured in second, and so on. So if we look here at this first part of the figure, the left-hand side, so we have here a gravitational free fall. So if we have a mass, this mass of 1 kilogram, if we set it free to just fall freely from a specific height near the surface of the Earth, so it is influenced by the gravitational acceleration. So we'll find that the weight or the force due to gravity on this particle is equal to 9.81 Newton. And the particle would start accelerating by the gravitational acceleration. So the acceleration here is A is equal to G is equal to 9.81 meter per second squared. If we just compare this to the US customary units or imperial units, we find that at the right-hand side here, if we have a mass of one slug, where they measure the mass in slug, it's equivalent to the kilogram in the SI units, which is 32.2 pound mass. So if we have here this particle with this specific mass, 32.2 pound mass or one slug, and we set it free from rest to just accelerate towards the ground. So we'll find that the force, due to the gravity, which is the weight, is 32.2 pound force, and the mass would accelerate with a specific gravity or acceleration, which is 32.2 feet per second squared. If we take a slightly smaller mass, which is the mass here is 1 pound mass compared to this mass, which is 32.2 pound mass. So if we take a smaller mass and then we perform the same experiment, we just set it to fall freely from a specific weight very near from the surface of the Earth, we'll find that the weight here or the force due to gravity is 1 pound force, and it would accelerate with the same acceleration, which is gravitational acceleration, in the imperial units or US units is 32.2 feet per second square. So the bottom part of the figure here, we have Newton's second law. So on the left-hand side, we have the SI units. So it's the definition of the Newton's second law using like figure. So if you have a mass of 1 kilogram and then you are applying a force of 1 Newton to this mass, so you'll find that this mass is accelerating by a value of 1 meter per second squared. It means that the speed will increase. The speed would increase by 1 meter per second for each second of the motion. If we look at the far right end of the graph here, we are using if we are using the US units or imperial units. If we have a mass of 1 slug, and then we are subjecting this mass to a force of 1 pound force, so we'll find that this mass would accelerate by 1 feet per second square. So it's the velocity would increase for each second would increase by 1 feet per second. So if we choose to study a smaller mass, which is 1 pound mass, and we apply the same force, so the force here again is like 1 pound force, it's similar to this force, but we just chose to use a smaller mass, we find that the acceleration here is increasing. It's 32.2 feet per second square. So if you remember from the Newton's second law, the mass and the acceleration, they are inversely proportional. So if we increase the mass, so the acceleration decreases. If we decrease the mass, so the acceleration increases. And here is the case. When we decrease the mass from 32.2 pound mass to 1 pound mass, we found that the acceleration has increased. It was increased from 1 feet per second square to 32.2 feet per second square. Excuse me. So generally here in the kinetic problems, we have two types of problems. The first type is that we have a known acceleration. The acceleration is known. Either it is given or can be calculated using the kinematics analysis. And the forces are calculated. So we are required here to calculate the forces. In this case, this problem is generally straightforward. We wouldn't find any problem with this kind of problem. So the second type is that if the forces are given, but the acceleration is required. So we have two cases here. The first case is that if the forces are constant, the forces are given and they are constant, it means that the acceleration is also constant, and this is easily found. So we will be able to find easily the acceleration. The second case is a bit challenging. So the forces are given, but they are function either of velocity, position, or time. So in this case, when we apply the Newton's second law, we get a differential equation. And in order to get the velocity, displacement, or acceleration, we might need to use the integration. This is the challenging part of the study of kinetics. So we have two types of motions. One motion, the first type of motion is called unconstrained motion. So in this case, for example, if we have a flight, so the flight is flying without any constraints, so it can move in the X, Y, or Z direction. So it can move in a specific direction, and we have the components of the velocity or the position or the acceleration in X and Y. X, Y, and Z directions. So this is unconstrained motion. But compared to the constrained motion, if you see the picture here on the right-hand side, we have a roller coaster where these carriages follow a specific path. So it's constrained to move along this the path of this structure. So it's constrained, can move only forward, but it cannot move to right or left or up or down. So we have a constrained motion here. So generally, we'll start by studying the rectilinear motion, and rectilinear motion means that the particle the particle follows a straight line, either it is in x direction, y direction, z direction, or inclined, but it is still like a straight line. So, for example, if the motion is constrained to the x direction only, so the particle can move in the x direction only. Like if we have a train, so the train moves forward only. So if we consider that this is the x direction where the train moves, so this is the direction of the motion. But the train cannot move to the left or to the right in the y direction. It cannot move up and down in the z direction. In this case, we will be applying the Newton's second law. So, but we see here that we have three components because the Newton's second law is a vectorial equation. It's a vector equation. So we have here, if we are studying the motion, using the rectangular coordinate system. So we have x, y, and z directions. So if we apply the Newton's second law in the x direction, it means that the resultant force in the x direction is equal to the mass multiplied by the acceleration in the x direction. Regarding the y and z directions, we say that the resultant force in the y direction is equal to 0 and the resultant force in the z direction is equal to 0. That's because the motion is constrained to the x direction. So we don't have any acceleration in the y direction, we don't have any acceleration in the z direction. So the acceleration in the y direction is equal to 0, the acceleration in the z direction is equal to 0. Oppositely, if we have unconstrained rectilinear motion, so we would have the three components. We can apply the Newton's second law in the x direction, where we have uh, the resultant force in the x direction is equal to the mass multiplied by the acceleration in the x direction. The resultant force in the y direction is equal to the mass multiplied by the acceleration in the y direction. The resultant force in the z direction is equal to the mass multiplied by the acceleration in the z direction. We don't have any constraints here. The motion would have acceleration components in x, y, and z directions. Meaning that the acceleration is equal to, as a vector, is equal to a component in the x direction, ax, component in the y direction, ey, component in the z direction, az. So if we wanted to get the total acceleration, in this case, it's the square root of ax squared plus ay squared plus az squared. Similarly, for the force, we have the force here as a vector. So the resultant force as a vector is equal to one component in the x direction, another component in the y direction, another component in the z direction. So we have sigma fx, sigma fy, sigma fz in x, y, and z direction respectively. If you wanted to get the resultant force, so the resultant force is equal to the square root of each component squared. So the square root of fx squared plus fy squared plus fz squared. So let's have three examples. We have three examples in this lecture here. The first example is that we have a 75 kilogram man. This man here stands on a spring scale. So we have a spring scale here in an elevator. So this is the cabin of an elevator as well. So, excuse me. So during the first 3 seconds of motion from rest, so the motion started from rest, so v sub 0 is equal to 0, and the duration of motion is only 3 seconds. The tension here in the hoisting cable is 8,300 newtons, so the force here that is pulling the cabin upwards is 8,300 newtons. Find the reading R of the scale. So we need to find here the reading of this scale, which is going to be the reaction force between the feet of this person and the scale. So which we call it capital R. So find the reading R of the scale in Newton during this interval, during the 3 seconds. And upward velocity V, so we would also need to calculate the velocity, the upwards velocity v of the elevator at the end of 3 seconds. The total mass of the elevator, man, and the scale is 750 kilogram. You see here that we have here two forces, the weight, which is the mass multiplied by the gravitational acceleration, which is 750 multiplied by 9.81 equals 7,360 Newton. We have another force here, the tension in the cable, which is 8,300 Newton. So because the forces here are constant, so we expect that the acceleration is going to be constant as well. And the first step in studying the kinetics or kinematics problem is to define the coordinates. What type of coordinates are you using? So in this case, the elevator goes up and down, so it's a rectilinear motion, so it can move. If we consider that this is the positive y direction, so it moves along the y direction. So we assume here that the elevator has an acceleration along the y direction, which is called a sub y. So if we started by studying the elevator, the man, and the scale all together, so we can apply the Newton's second law, which is the resultant force in the y direction is equal to the mass multiplied by the acceleration in the y direction. So we need here to find the resultant force in the y direction, considering that the positive y direction is going upwards. So we have a force here, T. The force T is going upwards, so it's 8,300 newtons. So this is our first force. We have another force here, the weight, which is 7,360 newton, or it's 750 kilogram mass multiplied by 9.81. It is going down, that's why it's negative, and this is equal to the mass, which is 750 multiplied by a sub y, which is the acceleration in the y direction. So the left-hand side here is giving us the sum of the forces. So if we calculate the acceleration here, so the a sub y, the acceleration in the y direction is 1.257 meter per second squared. And because the forces are constant, so the acceleration is constant. So it was required to find the reaction force or the reading on the scale. Or so if we started to study the person himself, so what are the forces applied to the person? We have the reaction force between the feet of the person and the scale, and we have the weight of the person. The person was 75 kilogram. If we multiply this by the gravitational acceleration 9.81, so this gives us 736 Newton. So again, the person is moving upwards by the same acceleration AY because he was inside in the cabin. So we apply the same equation. So the resultant force in the y direction, or the sum of the forces in the y direction, is equal to the mass multiplied by the acceleration in the y direction. In this case, we know the value of the acceleration in y direction from the previous step here. So we have the force R going up, so it's positive R, minus the other force, which is the weight, 736 newtons, is equal to the mass of the person, which is 75 kilogram, multiplied by the acceleration, which is 1.257. Based on this equation, we can find the reading of the scale, which is going to be 830 newtons. We still need to find the velocity, though, the vertical velocity or the upward velocity of the elevator at the end of the 3 seconds. Because the acceleration is constant, so we can use this equation. For example, A, which is the acceleration, is equal to dv by dt. And then here we just simplify this as dv is equal to the acceleration multiplied by delta t. So we integrate the left and the right hand sides. So we integrate here from 0 because the motion starts from rest. So the v sub 0 is 0. From 0 to v. And during the 3 seconds, so we start by time at time is equal to 0 to time is equal to 3 seconds. we see here that the acceleration is constant, so it's 1.257. So it's an easy it's an easy integration. So on the left hand side we have v from 0 to v, and the right hand side we have 1.257 t from 0 to 3. If we just substitute the limits of the integration, we get here the velocity as 3.771 meter per second. And because the acceleration is constant, so we can use the equations of motion that we've seen before straight away. So like the first equation, v is equal to v0 plus at. We know that v0 is 0, and we know the time is 3 seconds, and the acceleration is 1.257. So we can easily find here the velocity, which is going to be 3.771 meter per second. It's the same. So either you solve this part of the problem using the left-hand side or the right-hand side method. Another problem here. So we have an example too. We have a small inspection car. We have a car here. The mass of this car is 200 kilogram. It runs along the fixed overhead cable. So we have an overhead cable here. So this car runs along this cable, and it is controlled and is controlled by the attached cable at A. So we control the car either moving up or down using this cable, where the tension in the cable is 2.4 kilonewton. So determine the acceleration of the car when the control cable is horizontal. So this control cable is horizontal, and it is under tension T of 2.4 kilonewton. So we need to find the acceleration of the car. Also find the total force P exerted by the supporting cable on the wheels. So we have a couple of wheels here. So we need to find the reaction force, we call it P, between the cable and the car. So two things here. We need to find the acceleration of the car that is going in this direction along the cable, and we also need to find the P, which is the reaction force between the car and the cable. So we need to set up first the X and Y coordinate system. And you see here, this is the free body diagram of the car, where we have, remember, we have the tension here in the cable, which is 2.4 kilonewton. We have the weight of this car, which is the W is equal to mg, which is the 200 multiplied by 9.81, which gives us 1,962 Newton. And we have a reaction force between the car and the cable, which we call it P. So if we choose the X direction along the cable, so this is X, sorry, it is hiding here. So we have X direction along the cable, and we have the Y direction perpendicular to the cable. So all what we need to do here is to resolve the forces along the X and Y direction. So we'll just resolve these forces as we go along. Remember that it is given here the theta, the angle, but it is not given explicitly. This little triangle here is given. So if we take this triangle and we zoom it a little bit, so we have here 12, 5. So if we calculate the hypotenuse here, so we get the 13. So the slope here in the Y direction is given by the same triangle. So we have theta here, where we have this side as 5, this side as 12, and the hypotenuse is 13. So remember that this angle is theta as well. So the first step is to choose the coordinate system. So we chose here the XY coordinate system, and we can apply the Newton's second law. So the Newton's second law can be applied in two directions, in the Y direction and in the X direction. So excuse me. So if we start with the y direction, so we say that the sum of the forces in the y direction is equal to 0. Why it is equal to 0? Simply because the car cannot move in the y direction. It moves only in the x direction. So the acceleration in the y direction is equal to 0. In this case, we have here the force in the y direction. We have three forces. We have the reaction force P between the car and the cable, and it is exactly in the y direction. And we have two more components. The orange component here of the force is coming from the T, which is the tension in the cable. So if we resolve this force T in the y direction, so we are getting here, if this is theta, so we are getting here a component that is T sine theta. The T value is 2.4 kilonewton, so we need to multiply by 10 to the power 3 to convert it to Newton, and then we need to get the sine theta. So if you go to this triangle, you will find that the sine theta is 5 divided by 13. So the orange component in the y direction here is 2.4 multiplied by 10 to the power 3 multiplied by 5 divided by 13. If the positive y direction is going up, so P is going to be positive, and then the orange component here, which is the component coming from the tension in the tension in the cable along the y direction, is 2.4 multiplied by 10 to the power 3 multiplied by 5 divided by 13. We have another component coming from the weight, because the weight here is going vertically down, so we need to resolve this weight along the y direction. If we have this angle theta, so the component in the y direction here is going to be W cosine theta. So the W, which is the weight, is 1,962 Newton, and it is multiplied by the theta, cosine theta, where the cosine theta here based on this triangle is 12 divided by 13. So this component here is negative because it's going in this direction, where the positive direction of the y is going up. So this component is negative, and these are the three forces in the y direction with their signs. They are equal to 0, and you figure out here that based on this we can calculate the value of P, which is the reaction force between the car and the cable, which is 2,734.15 Newton. We still can apply the Newton's second law in the x direction as well. So sum of the forces in the x direction is equal to the mass multiplied by the acceleration in the x direction. So what are the forces in the x direction here? We have this component coming from the tension again in the cable. If this is the angle theta, so this component is the T cosine theta. So the T value, is the tension, is 2.4 multiplied by 10 to the power 3, and cosine theta based on this triangle here that is shown here. So the cosine is 12 divided by 13. So the force T multiplied by cosine theta. If we consider that this is the positive x direction, so this component of the force is going to be positive. So we have another component here that is coming from the weight. So the weight here, if this is the angle theta, so the component of the weight here in this direction is going to be W sine theta. So the W, or the weight, is 1,962 multiplied by sine theta, where the theta here, based on this triangle, sine theta is 5 divided by 13. So we go back to the equation and then plug in these values into the equation, where we have the component coming from the tension in the cable and the component coming from the weight, and they are equal to the mass multiplied by the acceleration in the x direction. The mass is 200. This is the mass of the car, and the acceleration in the x direction is a, which is unknown. So based on this equation, we can simply find the acceleration of the car in the x direction, which is 7.3 meter per second square, which is constant because all the forces here are constant. So the last example in this lecture is example number 3, where we have here a 125 kilogram concrete block A. So this block weighs 125 kilogram. Is released from rest. So this, when this block was released, the initial velocity was 0 in the position shown, and pulls the 200 kilogram log. So we have a log here. The weight of this log is 200 kilogram. It pulls the 200 kilogram log up the 30 degrees ramp. So this ramp is 30 degrees to the horizontal. If the coefficient of kinetic friction between the log and the ramp is 0.5, there is a friction between the log and the surface here on the ramp, and the coefficient of friction is 0.5, and we call it kinetic friction because it's moving. It's not static, it's just moving during the motion. The coefficient of friction is 0.5. Determine the velocity of the block. So this is the block A. So the velocity is required when it hits the ground at B. So what is the velocity of this block when it reaches the ground or hits the ground, given that the height here is 6 meters. So how we start this problem? So we start this problem by considering that the block moves downwards and the log moves upwards. Okay. So if we assume that the center of this pulley at C has the same velocity and acceleration as the log, so we can consider that the acceleration of C, velocity of C is the same velocity and acceleration as the log. So if we assume that the position of the C can be measured relative to a fixed center here, which is this pulley, the center of this pulley. So the distance here in this direction is called S sub C. So it's the position of C. And remember that the arrow here shows you the positive direction of this measurement. So if we assume that the block here going downwards is measured from the center of the same block, and it's measured as S sub A, which is the position of the block A. So, and here is the positive direction as well. So in this case, we start with a simple equation, which is the length of the cable. We know here that the length of the cable is constant, but we need to find the relation between the length of the cable and these parameters, the position S sub C and S sub A. So if we consider that the length of the cable L is equal to, you see here that we have double length here in this case. So it is equal to 2 multiplied by SC plus the value SA plus a constant. This constant coming from the rest of the cable, because we didn't account for this length, for example, that goes around the pulley. We didn't account for this length here that goes around the pulley. We didn't account for this length and so on. So we call them constant. But we know that SC, which is the position of point C, S sub A, which is the position of the block A, these are the variables. They change when the system moves. So for example, the SA becomes larger and the SC becomes smaller and so on. So these are the variables. But L, the length of the cable is constant. The constant here is any number. Okay. So if we differentiate this position or this displacement with respect to time twice, so we are getting here the derivative of L because it's constant. So the first and second derivatives will give us 0. When we get the first time derivative of the displacement, gives you the velocity. The second time derivative gives you the acceleration. So this is going to be 2AC, which is the acceleration of point C, plus A sub capital A, which is the acceleration of the block A. And the constant here, the time derivative of the constant is given as 0. So there is a relation here between the acceleration of the block A and the acceleration of point C, which is in turn the acceleration of the log. So the 2AC is equal to negative AA. So the acceleration here, this is equation 1, and the acceleration at point C is half of that at point A. Okay, and if we study the forces here, so let's start with the block here. So if the force is the weight force is going down here, so we'll assume that the tension in the cable is T. Okay, then this tension in the cable, if we go here, so this tension of the cable just moves to here where we have the pulley C. So for the pulley C here, on the top we have a tension in the cable T, and then because we still have the same cable around the pulley, so we have on the other side we have T as well. We have another tension here because this side of the pulley is attached to the center of this pulley, which is fixed, so we have kind of a reaction force. So for this pulley, if we are studying this statically, so we have tension here, T, we have another tension T here. So in turn, this force here, the tension in this part of the cable here is 2T, because here the all the forces in the x direction is equal to 0 because it's balanced. So in this case, the tension here is 2T, and consequently, due to the action under action, third Newton's law, so we have on the log here, we have a force that is pulling the log up, which is 2T. We have here the log, and there is a friction between the log and the ramp. So we have a friction force, and the friction force is related to the normal force. We have a reaction normal force in the y direction here, if we consider this is the y direction. If we consider the ramp is the x direction, so the N here is the reaction force between the log and the ramp, and the friction force. The friction force is equal to the coefficient of friction multiplied by the reaction force. So it's the coefficient of friction is 0.5, and the normal force or the reaction force is N. So it's 0.5 N. It's not 0.5 Newton. It's 0.5 multiplied by force called N, which is the reaction force or the normal force here. Okay. So we have another force here, which is the weight of the log, because the log weighs 200 kilograms. So if you multiply this by 9.81, so we get here 200 multiplied by 9.81 Newton here. This is Newton. Okay, so this is inclined. The inclined one here, or the italic symbol N is N, which is a force, and this one is Newton. Okay, we have an angle of 30 here between the vertical weight component here and the y direction. So this is the positive y direction. This is the negative y. So this is the positive x direction. So positive x direction along the ramp, positive y direction perpendicular to the ramp. So now we have one equation, the first equation that relates the acceleration of C to the acceleration of A. So for the log, we set up the xy coordinate system as shown, and then we can study the log here in the y direction and in the x direction. The log moves only in the x direction. It doesn't move in the y direction. That's why we say sum of the forces in the y direction is equal to 0. Our job here is to find the forces in the y direction considering the positive y direction that is going up. So we have here the reaction force or the normal force N. It's going up, that's why it's positive. And we have another component, the component that is coming from the weight along the y direction. It's going down to be, it will be going down. So in this case, it's going to be negative, and it is the weight multiplied by cosine 30. So the weight here is 200 multiplied by 9.81 multiplied by cosine 30, and this is equal to 0. Based on this equation, we can find the reaction or the normal force, capital N. We can now study the log in the x direction, where we say that the summation of the forces in the x direction is equal to the mass multiplied by the acceleration in the x direction. There is an acceleration in the x direction here because the log moves up the ramp, but it doesn't move in the y direction. So our job here again is to find all the forces in the x direction, considering that the positive x direction is going down here. Okay, so we have friction force 0.5 multiplied by n, where n was found in the previous step as 1,699 multiplied by the coefficient of friction, which is 0.5. This is our first force in the x direction, positive. We have another force going up, which is negative 2t. So we have here negative 2t as the force going up. And we have another component of the weight, because this weight will be resolved in the y direction and in the x direction. So the component of the weight in the x direction is shown in orange here, and it is going down, so it's positive. And it's the weight here, because we are just getting the component of this weight in this direction, so it's going to be the weight multiplied by sine theta. So the weight is 200 multiplied by 9.81 multiplied by sine theta, which is 30 degrees here, is equal to the mass of the log, which is 200, multiplied by the acceleration of the log in the x direction, which is AC. As we have agreed that the acceleration of the log is the same acceleration as the c, because this part of the cable here is can be considered as inextendable, it's rigid. Based on this equation, we have an equation, but we have two unknowns here. We have the acceleration c, we have the tension T. And then if we go to the first equation, we see that we have another unknown, which is the acceleration A. So we have three unknowns now: the tension T, the acceleration AC, and the acceleration AA. So we need three equations. So far we've got two equations. This is the second equation, so we require one more equation. The next equation can be found by studying the block. So if we study the motion of the block here, we say that this block moved in the vertical direction. If we consider that the y direction for this particular block, the y direction is going down, and don't mix up between this part and this part. We are studying them separately. So you set up another coordinate system for this part of the problem, or this block. So if we consider that the y direction is positive going downwards, and it's the same direction as the SA, so the SA is positive, that is going down, so we consider that the positive direction here for the kinetic part as well is going down. So we have here two forces. The first force is the weight of the block, which is 125 multiplied by 9.81, and the other for the second force is T. And because it's going up, so it's negative T. So summation of the forces in the y direction for the block is equal to its mass, which is 125, multiplied by the acceleration of this block, AA. And this is going to be our third equation. So we have three equations now. So the next step is to solve these three equations together to find the tension T, the acceleration of the block A, and the acceleration of the log AC. So this is our first equation that we've got, that 2AC is equal to negative AA. The second equation was this equation here. The third equation is this equation. So we have three equations now. We just need to solve these equations together by just direct substitution, or you can use your calculator to solve these three equations together to get the three unknowns. If we consider the last equation, which is equation number 3, if we substitute equation 1 into equation 3, so we'll take here the acceleration AA as negative 2AC, and then we'll plug it in here in this equation. We just replace AA by negative 2AC. So this is going to be equation number 4. no, sorry, not equation number 4. We just need to substitute the equation number 1 into equation number 3 to get this equation. And then we just kind of multiply the resulting equation here by 2 to just double this value to make it 2t as following. So if we multiply the resulting equation by 2, so we are getting this equation, which we call equation number 4. And then if you just compare this equation number 4 by equation number 2, you will find that we have 2t here, 2 multiplied by t, and we have 2 multiplied by t here. So we can subtract equation number 4 from equation number 2, and then the t here, the 2t cancels out, and then we'll be able to solve these equations together to get the acceleration AC. So, so if you subtract equation number 4 from equation number 2, so you are getting here the AC, which is the acceleration of the log, which is negative 0.888 meter per second squared. So this is our first unknown, the acceleration of the log. Again, because we have a relation between the acceleration of the log and the acceleration of the block, we can substitute this acceleration into the first equation to get the acceleration A, which is 1.777 meter per second squared. And then we can just substitute these two values into one of the equations, 2 or 3 or 4, to get the tension, which is 1004 newtons. This way we've got the acceleration of the log AC, the acceleration of the block AA, and the tension. We still need to find the velocity though. We can study only the block, and we say that V squared here is equal to V0 squared plus 2 AC. Then this is 2AA, no? 2AC, we'll change this one, but it's 2AA because we are studying the block. So the V0 here is 0 because it starts from 0, and the V here is required, and the acceleration, this is A sub A. So we'll just substitute A sub A here multiplied by 2, and it's giving us 4.62 after we get the square root. So we have here the velocity of the block. This was your portfolio problem for this week, and thank you very much.